For this question, we want to draw a picture, set up the proper integral, and find the area on your scratch paper. We want to find the area of the region between the two curves, f of x equals 2x squared minus 6x minus 10, and g of x equals 8 minus 9x plus x squared, from x equals 0 to x equals 2. I am going to use my calculator to help me get a good picture of this. So I've got my TI graphing calculator, and I'm going to type the first equation into the y equals menu. 2x squared minus 6x minus 10. And the other equation is 8 minus 9x minus x squared. Let's take a look at that graph. Okay, I'm not getting a good picture of it, so let me adjust my window. I have kind of a crazy window left over from last time, so let's hit zoom 6 to go back to the standard viewing window. Now I have a little bit better of an idea, but I'm not seeing the whole picture. So I'm going to zoom out a little bit. So let's zoom out. And now I can see my two curves here. So I've got the parabola that's facing down, which is this one right here, because it has a negative on the x squared. I know that's the one that's facing down. And then one that's facing up, that's the first one. So let me get a quick sketch of this. It doesn't have to be completely exact. So it's something like this. And we know that our top curve here is our parabola that's facing down. That's g of x. And our bottom curve is the one that's facing up. That's the f of x. And we're interested in finding the area between these two curves from x equals 1 to x equals 2. So we're also going to be bounded by vertical lines at x equals 1, x equals 0 and x equals 2. So we're really looking for a region that looks something like this. So when we set up our integral, we want to set it up with our top curve minus the bottom curve. And we saw that the parabola that's facing down is our top curve, the one that's higher up. So we'll have 8 minus 9x minus x squared. That's our top curve minus our bottom curve of 2x squared minus 6x minus 10. And we need to put our bounds from 0 to 2. So this is the proper setup. We've got our top curve minus our bottom curve inside the integral, and our bounds going from 0 to 2 along the x-axis. So then we need to do a little algebra to simplify before we try to find the integral. I would distribute that negative to make this minus 2x squared plus 6x plus 10. Dx. Then I can combine like terms. And I have a negative x squared and a negative 2x. That's a negative x cubed, negative 3x cubed, excuse me, negative 3x squared. And for our x's, we have a negative 9x and a positive 6x, so that will be a minus 3x. And then for our constants, 8 and 10 combined together to be 18. And now we're going to find our antiderivative. That'll be a negative 3x cubed over 3 using the power rule, minus 3x squared over 2, also using the power rule, and 18x. And we're going to evaluate this from 0 to 2. We can simplify before we evaluate using that fundamental theorem of algebra. Excuse me, the fundamental theorem of calculus. And that would give negative x cubed minus 3 over 2x squared plus 18x and we're going to evaluate that from 0 to 2. So using our fundamental theorem of calculus, we're going to evaluate at the upper bound and evaluate at the lower bound and subtract those two values. Since that lower bound is 0, when we plug in, we'll get 0. So that part is going to be simple to simplify. We have negative 2 cubed minus 3 over 2 times 2 squared plus 18 times 2 minus negative 0 cubed minus 3 over 2 times 0 squared plus 18 times 0. So I guess that all of this is 0. And over here we have 2 cubed is 8. That's a negative 8. And one of these 2's cancels out, so we have a minus 6. Plus 18 times 2, that will be 36. We have 36 minus 14 will give 22. So we have the area between these two curves, which is also bounded by x equals 0 and x equals 2, to be 22. For this question, we want to solve the problem using calculus techniques. We want to show our work on scratch paper. And the question we're addressing is to find two positive numbers whose product is 144 and whose sum is minimum. So what we're going to do is establish variables for the two positive numbers. So I'll let the first number be x and I'll let the second number be y. We're given that the product of these numbers is 144. So if I multiply those two numbers together, I'm going to get a result of 144. And we want to find these two numbers so that the sum is minimum. So the sum of these two numbers, x plus y, needs to be minimized. And that's where our calculus techniques come into play. We have a process where we can find the minimum value using calculus techniques. However, we have one problem at this moment, and that is that we have too many variables in the equation that we want to minimize. So we can use this other information about the two numbers, and we're going to solve for one and substitute in so that we can reduce the number of variables in the problem. So I can solve for y and write this equation as y equals 144 over x, and substitute that in for y. And now I have an equation for the sum, which only has one variable, and that's x plus 144 over x. For calculus purposes, it's easier for us to work with the equation in this format, x plus 144 x to the negative 1. So we're going to follow our process for finding the minimum value, and that is to calculate the derivative and find the critical numbers. So the derivative of x is 1, and we have 144 being a constant multiple, and the derivative of x to the negative 1 is negative 1 x to the negative 2. That's 1 minus 144 over x squared. So now I'm looking for the critical numbers, and the critical numbers are where our derivative is equal to 0 or our derivative is undefined. So if we set our derivative equal to 0, we'll have the equation 0 equals 1 minus 144 over x squared. I'm going to add the 144 over x squared to the other side. And that gives me 144 over x squared equals 1. I can multiply both sides by x squared to get the equation 144 equals x squared. Square root both sides. And that gives me solutions of x equals plus and minus 12. So we have critical numbers of positive and negative 12. Now we do have some concerns for this derivative being undefined because we have a variable in the denominator. So if we set that denominator equal to 0, we can see that we have another critical number of 0. So our critical numbers are x equals 0, negative 12, and positive 12. Now, as far as solutions to this problem, we know that we can eliminate 0 and negative 12 because the question describes the numbers as positive numbers. So 0 is neutral, it has no sign, and negative 12 is negative. So 12 is the only one that we're considering to be a solution to this problem. And then we want to see if it actually produces a minimum value. So in order to do that, we're going to look at the second derivative test. So let me write the first derivative in a nice way. So that's 1 plus, that would be 1 minus 144 x to the negative 2. And we're going to calculate the second derivative. The derivative of 1 is 0. Negative 144 is a constant multiple. And we'll calculate the derivative on x to the negative 2. That's negative 2 x to the negative 3. And so this gives us a positive 288 over x cubed for our second derivative. And if we evaluate that second derivative at our critical number of 12, we're going to get 288 over 12 cubed, which is a positive number. When the second derivative is positive, we know that our function is concave up at that point. And concave up combined with the fact that we're working with a critical number means that we're dealing with a minimum value. So we can say that our critical number of 12 is going to be our minimum value. So that's the value that we got for x. And you can substitute that 12 in. 144 over 12 is 12. So we also get 12 for the second number. So the numbers that we were looking for are 12 and 12. The product of these numbers is 144, and they produce a sum whose minimum. For f of x equals 5x squared minus 3x plus 1, we want to find the equation of the tangent line when x equals 2. And we want to write the equation in slope-intercept form. So a couple things that we need to keep in mind is that we can use algebra to write an equation of a line, and we're going to use y minus y1 equals m times x minus x1. So in order for us to do the algebra, we have to know an ordered pair. That's x1, y1. That's going to be a point that's on the line. And then we also have to know the slope of the line. So we are given x equals 2. So we know the value that we're going to plug into x1. We don't know the slope and we don't know the y value. But we can easily get the y value by substituting 2 into our function. That would be 5 times 2 squared minus 3 times 2 plus 1. That's 5 times 4 minus 6 plus 1. 20 minus 5 would be 15. So we know that this 15 is what we substitute into the y1. So where the calculus comes in is with the slope of the line. The slope of the line is the derivative. So we're going to calculate the derivative of our function, and the derivative will give us the slope at any particular point. So let's calculate the derivative for f of x, and f prime of x would be 10x minus 3, and we want to evaluate the derivative at that value of 2. That's 10 times 2 minus 3 would be 20 minus 3 is 17, and now we have the value that we're going to use for the slope as well. We're going to substitute all those values into the equation. This format is called point slope form. And of course, there are other ways to get the equation of the line as well. So we're going to do y minus 15 equals 17 times x minus 2. And I want to manipulate this to put it into slope-intercept form. Slope-intercept form is y equals mx plus b. So I'll distribute this 17, and that will give me 17x minus 34. And I'll add 15 to both sides, and that gives y equals 17x. And let's see, I'm going to have to borrow to get 19, negative 19. So we have y equals 17x minus 19 being the equation of the tangent line at x equals 2. We want to use the limit process to find the area of the region bounded by the graph of the function and the x-axis over the given interval. We're going to sketch the graph so that we can get a good idea of what area we're finding. We have the function f of x equals negative 4x plus 5. We want to find the area on the interval from 0 to 1. So this function is a linear function. It has a slope of negative 4 and a y-intercept of 5. Let's take a look at our picture. So we would plot the y-intercept. We're going to use the slope, so I'm going to go down 4, 1, 2, 3, 4, and over 1. And connect those 2 points with a straight line. So we're interested in finding the area from x equals 0, there's the vertical line x equals 0 to x equals 1. So we're looking for the area from this curve to the x-axis. So we can set up a definite integral to represent this area. So that's going to be the integral of our function and we're going to be bounded from 0 to 1. So we have the integral from 0 to 1 of negative 4x plus 5 dx. Now we could find this definite integral very easily with the fundamental theorem of calculus, but these directions specifically say to use the limit process. So I'm going to give you the definition of the definite integral using that limit definition. So you can see here that we define a definite integral using this limit sum definition. So our goal is to find the area not with the shortcut, the fundamental theorem of calculus, but with this definition of the definite integral. So it's going to take a little bit of work to set this up properly. So let's figure out what these different pieces mean. We're going to simplify the definition just a little bit. So let's start with what these different components stand for. So this part right here, the delta xi, this is where we create rectangles, and this delta x sub I represents the width of each one of those rectangles. So it allows for each rectangle to be different widths, but we're going to simplify it down to having the rectangles be of equal width. So instead of using delta x sub I, we're just going to use delta x. We're going to use a constant width for all of the intervals. If we use a constant width, we're going to take our upper bound minus our lower bound and divide it into equal intervals. So for us, we have b minus a, our upper bound of 1 minus our lower bound of 0 over n. So we get that our delta x is 1 over n. So this ci here is representing a sequence of points that we use in each one of the rectangles. And to simplify it for us, we're just going to use the right endpoints of the intervals of those rectangles. So this gives us the simplest formula to work with algebraically. So our CI, our secret sequence of points for all of those rectangles, is going to be A, that's our lower bound, plus delta x times I. So this will give us a sequence of right endpoints. Our lower bound is 0. We just found our delta x to be 1 over n, and we have that multiplied by I. So our sequence of right endpoints for our rectangles will be just I over n. Another simplification that we're going to make is that this part right here in the definition has the norm approaching 0. Because we have simplified this problem down to have equal rectangles, we can simplify the part here to just say n approaches infinity, because that will be the same thing as the norm going to 0. So we're going to change this part to be the limit as n approaches infinity. So let's write out some of the information that we have adjusted here. We've got our integral from 0 to 1 of negative 4x plus 5 dx is now going to be the limit as n approaches infinity. The sum of I equals 1 to n. F of our sequence of right endpoints, that's f of I over n, times delta xi, which we've simplified to be 1 over n. So we're going to substitute I over n into our function. Our function is negative 4x plus 5. That will give us the limit as n approaches infinity. Sum I equals 1 to n of negative 4 times I over n plus 5. Let's do a little bit of algebraic cleanup inside that summation. We would have the limit as n approaches infinity. Sum I equals 1 to n. And I can write this as negative 4I over n plus 5. And I also want to distribute that 1 over n. That would give the limit as n approaches infinity. Sum I equals 1 to n. Negative 4I over n squared plus 5 over n. And all of that's inside the summation. And now I can apply the sum to these individual terms. We can write this as the limit as n approaches infinity. And I'll go ahead and factor out the constants as we do this as well. So I'm applying the sum to the individual terms and factoring the constants out of the sum. So that would be negative 4 over n squared, sum I equals 1 to n of I, plus 1 over n, sum I equals 1 to n of 5. And we have some summation formulas which will allow us to work out what these pieces are. So let me get a screenshot of those formulas so you can see which ones I'm using. So the two formulas that we're going to be using are sum of a constant and sum of I. So this would simplify to be the limit as n approaches infinity, negative 4 over n squared. The sum of I is going to change to n times n plus 1 over 2. And the sum of a constant is that constant times n, so this becomes 5n. And we've applied the sums. We'll do a little bit of algebra cleanup. We've got the limit as n approaches infinity of negative 4n squared minus 4n over 2n squared, plus those n's cancel out, so we have just a 5 there. So when we're applying the limit on this, we have a limit approaching infinity. N is approaching infinity. So I can use a strategy of breaking up this into separate fractions. That would be negative 4n squared over 2n squared minus 4n over 2n squared plus 5. Those n squareds cancel out. We have negative 2 minus 2 over n plus 5, and as we apply the limit going to infinity, this portion is going to approach 0 because you have your denominator going to infinity and your numerator staying fixed, so that overall fraction goes to 0. So this gives us a limit of 3. So we found the definite integral, the area from negative 4x plus 5 to the x-axis from 0 to 1. And just to do this with the shortcut method would be using the fundamental theorem of calculus. You would find the antiderivative, that would be negative 4x squared over 2 plus 5x, and you're going to evaluate that from 0 to 1. This reduces to negative 2x squared plus 5x. From 0 to 1, you're going to evaluate at the upper bound, negative 2 times 1 squared plus 5 times 1, minus the lower bound evaluation, that's negative 2 times 0 squared plus 5 times 0. And this becomes negative 2 plus 5 minus 0, which is 3. Evaluate the indefinite integral, and the integral of 2x over x squared minus 9 cubed dx. So on this question, I'm noticing that we have an expression inside the parentheses, and so we might need to use substitution to do this problem. So that is a common way to use that substitution method, is to just to notice if you have something in the denominator or something inside a radical, something inside of parentheses. So we can try letting u equal x squared minus 9. We would calculate the derivative of that. Du over dx is 2x. And I'll rearrange this to solve for the dx. So I would multiply by dx on both sides. I would divide both sides by 2x. And that gives dx equals du over 2x. And I'm going to make two substitutions. One is for what's inside the parentheses, the x squared minus 9. And then the second substitution I'll make is for the dx. And that's du over 2x. So when I make that substitution, I would have 2x over x squared minus, I want to substitute. So it would be 2x over u cubed times du over 2x. Now the 2x's are going to cancel, and hopefully this will show you which antiderivative rule you're going to use to solve the problem. So I've got 1 over u to a power, and so I'm going to use the power rule to find the antiderivative. So that would be the integral of u to the negative 3 du. And using the power rule, we would have u to the negative 2 over negative 2 plus c. I want to bring back the original variable, so that u that I substituted earlier will be used. So I'll change it back to x squared minus 9, and that gives x squared minus 9 to the negative 2 over negative 2 plus c. And I just want to write this a little cleaner. We don't like to have negatives in the exponent, so I'd write this as negative 1 over 2 times x squared minus 9 squared plus c. Okay, you could also do this problem without substitution, with pattern recognition. So you'll notice that with pattern recognition, you would still need to think of x squared minus 9 as your u. And then when you calculate the derivative of that, you recognize the 2x is in the problem. So you could write this as x squared minus 9 to the negative 3 times 2x dx, and this fits the pattern of the general power rule. You have something to a power and then the derivative of that something within the problem. So you can apply the general power rule and add 1 to that exponent and divide by that same exponent plus c. And you get your solution of negative 1 over 2 times x squared minus 9 squared plus c using pattern recognition. For this question, we are given the equation y equals 2x to the 2x, and we want to use logarithmic differentiation to find the derivative of y. So with logarithmic differentiation, we would take the log on both sides. We're doing a little bit of algebra first so that we get it in a format where it's easier to calculate the derivative. So we have natural log of y equals natural log of 2x to the 2x. Now, for us to easily take this derivative, we need this variable that's in the exponent to come out of the exponent. However, we can't do that until we expand this logarithm. This 2, that's the coefficient, prevents me from applying one of my algebra log rules. So I want to expand the log first. This is using the product rule for logarithms. So this is natural log of x plus natural log of x to the 2x. And now that we have gotten rid of that coefficient of 2, I can apply the power rule for logarithms And the power rule for logarithms allows me to take that exponent and move it into the coefficient. So that would give natural log of y equals natural log of 2 plus 2x natural log of x. So far I've used algebra properties and log properties to simplify the equation. But we've rewritten the equation in what's called an implicit form. It started off with an explicit form. Explicit is when you have one variable in terms of the other, so that's y equals. But we've now manipulated it into an implicit form. And so when we calculate the derivative, we're going to use implicit differentiation. So I'm going to calculate the derivative with respect to x on the left and the derivative with respect to x on the right. On the left, if you pay attention to the variables, they don't match. So I'm going to have to write this as y prime over y. The derivative of natural log, the rule is u prime over u. The derivative of the inside over the inside. And since I don't know what y is, I can't calculate the derivative. Well, I guess that's my goal in this problem, is to calculate the derivative of the inside. Then we've got on the right-hand side, the variables do match, so we're going to take the derivative like normal. The derivative of a constant is 0. And then on this second term here, I've got to use the product rule. I'm going to do the first times the derivative of the second. Derivative of natural log is 1 over x, plus the second times the derivative of the first. The derivative of 2x is 2. So this gives y prime equals, y prime over y equals, the x's cancel out, so we have 2 plus 2 natural log x. And then I'm going to finalize this by solving for y prime. So I'll multiply by y on both sides. That gives y prime equals y times 2 plus 2 natural log x. And at the beginning, remember, we had the equation written explicitly. We had y equals 2x to the 2x. And so I can substitute so that I only have variables of x on the right-hand side. That would be 2x to the 2x times 2 plus 2 natural log x. And there's one more thing that I can do here. We have factors of 2 inside the parentheses, so I can factor those 2's out and make this a 4. And that would be 1 plus natural log x left. So we found that the derivative of 2x to the 2x is 4x to the 2x times 1 plus natural log x. On this example, we want to use logarithmic differentiation to differentiate the function with respect to x. So with logarithmic differentiation, we're going to calculate with a log on both sides. This is an algebra step that allows us to simplify the expression. So I'm doing natural log on both sides, and I'm going to go ahead and write this radical as a power. We'll write 2x squared plus 3 to the 1/2 power. And then we're going to apply the product rule for logarithms. It allows us to expand this log into x to the 5th plus 5 squared. plus natural log of 2x squared plus 3 to the 1/2. And then I'll use another log property, which is the power rule for logarithms. It allows me to bring these exponents to the coefficient, so that's 2 natural log of x to the 5th plus 5 plus 1/2 natural log of 2x squared plus 3. And now that I've got it fully expanded, I'm going to calculate the derivative with respect to x on both sides. So I have the derivative with respect to x of natural log y, the derivative with respect to x of 2 natural log of x squared plus 5 plus 1/2 natural log of 2x squared plus 3. Calculating the derivative on the left, we're going to follow our natural log rule, u prime over u, so that's y prime over y. On the right-hand side, we're also following the natural log rule, but since the expression inside is known, we're actually going to be able to calculate the derivative. So our derivative of the inside is 2x over the inside, and the derivative of the inside would be 4x over the inside of 2x squared plus 3. I'll go ahead and do a little bit of algebra cleanup. We have 2 times 2x would be 4x over x squared plus 5. The 2's cancel, giving us 2x over 2x squared plus 3. And it looks like I made a change here. I changed this x to the 5th to x squared here, so let's make that correction. So this should be x to the 5th plus 5. And then also when I calculated the derivative, instead of it being 2x, it should be 5x to the 4th. So this should be 5x to the 4th here, making this 10x to the 4th. Thank you for helping me correct that. So it's not necessary for your test, but for just making the algebra as simple as possible, I'm going to go ahead and get a common denominator and combine these two fractions together. So to do that, I would get 10x to the 4th over x to the 5th plus 5, and I'm going to multiply that by 2x squared plus 3 over 2x squared plus 3. Then on the second fraction, I have 2x over 2x squared plus 3, and I'll multiply that by x to the 5th plus 5 over x to the 5th plus 5. This is going to allow me to get a common denominator. I'll go ahead and distribute for the top, and I'll have 20x to the 6th plus 30x to the 4th plus 2x to the 6th plus 5, that would be a 10x. And all of this over the common denominator of x to the 5th plus 5 times 2x squared plus 3. I have y prime over y equals, let's combine like terms, that's 22x to the 6th plus 30x to the 4th plus 10x over our common denominator of x to the 5th plus 5 times 2x squared plus 3. We we have y prime over y in the numerator. I have a common factor of 2x. That would leave 11x to the 5th plus 15x cubed plus 5 over our common denominator of x to the 5th plus 5 times 2x squared plus 3. And so I'm going to now solve for y prime by multiplying by y on both sides. So y prime equals y times 2x times 11x to the 5th plus 15x cubed plus 5 over x to the 5th plus 5 times 2x squared plus 3. And if you'll remember at the beginning of the problem, our equation was written explicitly, so we do know what y is. So y is x to the 5th plus 5 squared times the square root of 2x squared plus 3. So we can write this as x to the 5th plus, x to the 5th plus 5 squared. And I'm going to write 2x squared plus 3 to the 1/2 power times 2x times 11x to the 5th plus 15x cubed plus 5. And all of this is over x to the 5th plus 5 times 2x squared plus 3. We have some canceling that happens. One of these factors of x to the 5th plus 5 cancels. And when I combine these two factors of x squared, 2x squared plus 3, I'm going to subtract those exponents. 1/2 minus 1, so this exponent, and this is an exponent of 1. 1/2 minus 1 is negative 1/2. So the negative tells me that factor is going to be in the denominator. So I have a factor of 2x squared plus 3 in the denominator raised to the 1/2 power. In the numerator I have 2x times x to the 5th plus 5 times 11x to the 5th plus 15x cubed plus 5. And the only final thing you could do is to change that radical, change that fractional power back to the radical form. So we could have 2x times x to the 5th plus 5 times 11x to the 5th plus 15x cubed plus 5 over the square root of 2x squared plus 3. So we've calculated the derivative using logarithmic differentiation. We want to solve the problem using calculus techniques. We have a liquid form of penicillin manufactured by a pharmaceutical firm is sold in bulk at a price of $200 per unit. If the total production cost in dollars for X units is C of X equals 500,000 plus 80X plus 0.003X squared, and if the production capacity of the firm is at most 30,000 units in a specified time, how many units of penicillin must be manufactured and sold in that time to maximize profit? Now, profit is calculated using the formula. Profit is revenue minus cost. So before we can calculate profit, we need to figure out what revenue is. And there's a business formula for revenue, and that is X times P, where X is the number of units and P is the price. So the price per unit is $200. So our revenue will be X times P, that's X times 200. So we have a formula for revenue being 200X. So then we can figure out the profit because we were given the cost function here. So our profit will be the revenue, 200X, minus the cost, 500,000, plus 80X, plus 0.003X squared. We'll distribute that negative and also combine like terms. This will give us negative 0.003X squared. We have a positive 200X and a negative 80X combining together to be a positive 120X, and then a negative 500,000. So this gives our function representing profit. So this is where our calculus techniques come into play in part C. We want to know how many units of penicillin must be manufactured and sold in that time to maximize profit. So to find the maximum, we're going to use our calculus technique, calculating the derivative of our profit function. The derivative of our profit function will be negative 0.006x plus 120. We're going to find our critical numbers by setting that equal to 0. We don't need to worry about it being undefined since this is a polynomial function. We'll subtract 120. It's negative 0.006. X equals negative 120. We'll divide both sides by negative 0.006. And we get X equals 20,000. So here's our critical number, and we want to know if this critical number actually produces a maximum. We're going to calculate the second derivative of our profit function, which is negative 0.006. And this is always negative. When the second derivative is negative, we know that the function is concave down. And that being combined with our critical number means that we've produced a maximum value. So we are going to have a maximum profit when our factory produces 20,000 units of our penicillin. Thank you for checking out my videos. Have a great day.